Good day. I am Ramunas Levinas from Vilnius University, Lithuania, and I'd like to thank you for tuning into my presentation on the application of intensity-modulated photocurrent and photoelectrochemical impedance spectroscopies for characterization of tungsten oxide, but also photocatalysts in general. Now, a short introduction. Transition metal oxides have many interesting electron photocatalytic properties, and amongst other things are being widely investigated as photoanodes for oxygen evolution. In this study, we obtained tungsten oxide films by anodization of tungsten in a fluoride ion electrolyte. The films are nanoporous, as shown by the surface morphology images on the right, and they are highly photoactive. But the operation of photocatalysts is not simple, and many considerations have to be kept in mind, as shown in this schematic representation of a photoelectrochemical cell. The space charge layer is arguably the most important part because here the absorbed photons generate electron-hole pairs, which result in fluxes of majority and minority charge carriers. Near the surface, recombination can occur, which has a detrimental effect on the catalyst's activity. The semiconductor electrolyte interface is equally as important because the photocatalyzed reaction proceeds on the material's surface through a certain mechanism, typically based on the absorption of an active species to the surface. The electrolyte should also be carefully selected, for example, the usage of hole scavengers to suppress recombination. And even the illumination must be adjusted suitably. The light should have enough energy to photoexcite the semiconductor material's electrons, and the reaction rate will depend on illumination intensity. I will not discuss all of those variables, but instead here I will briefly mention two non-stationary measurements that can be used to gain important information about the space charge layer and to an extent the semiconductor electrolyte interface. Those methods are, as you know from the title, photoelectrochemical impedance spectroscopy and intensity-modulated photocurrent spectroscopy. In PIS, the cell is illuminated, but light intensity is kept constant, and the cell potential is being modulated. Conversely, in IMPS, potentiostatic conditions are applied on the cell, and modulation is applied on the light intensity. Then, according to the Gartner equation, in PIS, the signal will be related to modulations in the width of the space charge layer, and in IMPS to modulations of the incident photon flux. Interpretation of photoelectrochemical impedance spectra is slightly nuanced, because a large photocurrent does not necessarily equal a low impedance. To understand this, we must examine photocurrent polarization curves. Here, a tungsten oxide sample was subjected to chopped UV illumination during a linear potential scan. The red line can be inferred as the dependence of photocurrent on potential, and the black line is the dependence of background current on potential. Looking at the background current, it is obvious that the curve is flat, and consequently, the system's impedance is almost identical at 1.2 and 2 volts. However, the red photocurrent curve has a certain slope to it, and at the respective potentials, the slope is different. The system's impedance increases with applied potential, and this is because at increasingly anodic potentials, the space charge layer expands less and less until the photocurrent would ideally plateau. Unlike PEIS, IMPS is an admittance spectroscopy method, which means that conductivity is measured rather than impedance. The IMPS transfer function is written with respect to rate constants of hole transfer across the space charge layer and recombination at the semiconductor electrolyte interface. A set of typical spectra obtained for tungsten oxide films is shown here. The spectra had been measured at the potentials indicated on the polarization curve shown above. The values of the real axis are ultimately related to photon conversion efficiency, and a broader semicircle corresponds to increased conversion efficiency. If these films had surface recombination of photo-generated holes, we would expect to see a semicircle in the first quadrant of this complex coordinate plane. The lack of this signal is fairly positive. These films have no surface recombination. The maximum angular frequency of this semicircle would be equal to the sum of transfer and recombination constants, and the low-frequency intercept with the axis is also a ratio of these constants. The conclusion that can be drawn from these spectra are that there is no recombination and that all photo-generated holes are transferred into the electrolyte. To conclude, further processing of PEIS and IMPS spectra could provide various parameters of the space charge layer and the semiconductor electrolyte interface, and even hint towards the reaction mechanism. All of this would complement and can be fundamentally related to steady-state measurements. Thank you for your attention, and feel free to email me should any ideas or questions arise.